Hello and welcome to Lecture 7 for the course ECE 257A, Fault Tolerant Computing. This lecture covers two chapters in the textbook, Chapter 9, Fault Testing, and Chapter 11, Design for Testability. The next lecture, Lecture 8, will deal with fault masking, Chapter 10, and Chapter 12, Replication and Voting. Okay, so first, the topic of fault testing. Fault testing is when we try to detect faults, logic faults in a circuit by forcing those faults to generate errors. In other words, we try to force this transition from the faulty state into the erroneous state so that we can observe the errors and based on our observations then deduce the presence of fault in the circuit, and in some cases actually determine what fault, what part of the circuit is faulty. But that part is not necessary, because when we know that the circuit is faulty, that may be enough, because we just replace the entire circuit. We don't need to find out exactly what part of the circuit is faulty. Okay, so we are now entering into our discussion of this faulty state. The first item of business is fault testing. And then fault masking is basically the collection of methods, strategies that allow the system to remain in the faulty state despite the presence of faults. In other words, we prevent the system from going from the faulty into the erroneous state, so that the faults, even though they're there, they don't generate errors and the system can continue its operation. Okay, now fault testing is a fairly extensive area of study. There are many different types of faults. The three types that we are the three types of fault testing that we are most interested in are engineering, testing for engineering faults. This is basically when we try to determine whether the system has a correct design at the time of the engineering design. In manufacturing fault testing, that's basically when we try to determine whether we have implemented the circuit or system correctly. And maintenance fault testing is when we try to determine whether the circuit is operating correctly. And no matter which type of fault testing or which type of fault we are interested in, the process of fault testing is the same. There are three parts to fault testing: test generation, test validation, and test application. So test generation can be preset, meaning that we determine all the tests ahead of time before we validate and apply them. Adaptive is when the generation of one test depends on the circuit behavior during the previous tests. So depending on the outcome of previous tests, we apply different tests in subsequent steps. Now, test generation can be functional or structural. Functional, basically, we use the circuit or system being tested as a black box. We either don't know or don't care about the internal structure of the circuit. So for example, if we are testing an adder, we test the addition function. We don't care how the addition is performed inside the circuit. Functional tests are often not very practical because they require a large number of tests. So imagine if you want to test a 32-bit adder, which has a total of 64 input bits, two 32-bit operands. And if you want to test it exhaustively for all possible inputs, you have a very large number of inputs to apply, which is 2 to the 64, which is impractical. So when you do functional testing, you have to come up with inputs that are most likely to create problems for the circuit. And that's a difficult thing to do. You have to come up with a set of inputs that exercise the circuit in such a way that makes it more likely to detect internal faults. Okay, structural testing is more common. Basically, you design your test, you generate your test based on your knowledge of the structure of the circuit. So if you're testing an adder, you know whether it's a ripple carry adder or carry look ahead adder, or what type of design of a carry look ahead adder. And that allows you to target your tests to basically determine whether the internal parts of the circuit are operating correctly. Now for structural test generation, we need to start with a fault model, then decide on fault coverage. Fault model, basically what can go wrong in the circuit. Coverage, what fraction of the faults am I aiming to detect? Of course, ideally coverage will be 100%, but that may be impractical, so we may be satisfied with a coverage of, say, 99%. The diagnosis extent, basically, do I want to be able to determine what's wrong in the circuit, or am I aiming for just what is known as a go, no-go test? I just want to determine whether the circuit is okay or not okay. I don't care. If something is wrong, I don't care what is wrong. I just replace the circuit. And then basically the algorithm for structural test generation. And we'll see a couple of these algorithms, the algorithms and Boolean difference in subsequent slides. Now, test validation can be theoretical. We mathematically prove that these tests are appropriate for detecting the faults that we are interested in, or can be experimental. Experimental can be done through simulation. We simulate faults and then see that the tests that we have designed actually detect those faults. Alternatively, we can do fault injection. This is basically when we go into the circuit and purposely insert faults. We disconnect some wires or do something to the circuit and then see whether our tests detect that. Typically, fault injection will be done by a team different from the team that designed the test. It should be independent so that we have a high confidence that our tests are appropriate. So basically, a team goes and makes parts of the circuit faulty, injects faults, and then we apply the test. And if the tests detect those purposely injected faults, then it will increase our confidence in the coverage or appropriateness of the test. Finally, test application can be externally controlled or internally controlled. Externally controlled, as the name implied, we externally apply tests to the circuit, and this can be manual application or automatic. application. These are basically techniques for automatic test equipment. So we insert an IC chip into this ATE unit, and the unit automatically applies tests to it and observes the behavior. And from the behavior, judges whether the particular circuit is faulty or not faulty. Internally controlled can also be of two kinds. When the circuit has internal test generation and application equipment, it may go into a special test mode. And all these three types of test application strategies are known as offline testing. The circuit goes offline, it basically abandons its normal operation and goes into the test mode. Alternatively, and this is much harder to do, we may aim for concurrent testing. Basically, testing occurs as the circuit is performing its normal function. And these tests like these are much more challenging, more difficult to design. Okay, so this is basically an overall view of testing. We will focus on structural testing, this part that has been highlighted, and we'll see some examples of methods in that category. Okay, so this is the test setup. We have a circuit under test, CUT, and there are some faults that can occur in this circuit. So for example, this point in the circuit may be faulty, and the type of fault depends on the fault model that we are assuming. In order to be able to detect this fault, we must be able to control that point through the inputs, circuit inputs. So there must be some controllability of that point. And then we must be able to observe that point through the primary outputs of the circuit. So this is part of the observability. So in order to be able to test a point in the circuit, we need controllability, good controllability, and good observability. And we'll define these a little bit more precisely later on in this lecture. Then we apply a test pattern. From test pattern source can be just a table where all the tests are stored, or it can be some random generator, test pattern generator. And then the output of the circuit is compared against some reference value. And if it matches the reference value, it passes the test. Otherwise, it fails the test. Now, the reference value can also come from a table. So a particular test, we know what the correct output of the circuit should be. We read it out from a table. Or it can be a copy of the circuit over here that we are sure it's fault-free. Sometimes this is known as the gold version of the circuit. So a gold version of the circuit is sitting here and receives the same inputs as this circuit under test. And then the output of that gold version that we know is correct is compared to the output of this circuit under test. And if they match, it passes the test. Sometimes in order to reduce the volume of data, rather than compare each output of the circuit to a reference value and make a judgment for it, we combine the outputs into what is known as a signature. So let's say this circuit generates a 32-bit number. Okay, rather than compare each 32-bit number to a 32-bit number reference value, and then basically have a bunch of comparison results, we combine these outputs into a single signature. Let's say we XOR all the 32-bit outputs from the circuit and get a 32-bit number at the very end of the test process. And that's known as the signature of the circuit. And that signature then is compared against a reference signature. So that reduces the number of comparisons. Of course, there's a small chance that even though the circuit is not operating correctly, the signature actually matches the correct signature. Because basically the incorrect values, when combined, cancel each other, and we lose the information about the fact that something is wrong. But that usually doesn't happen. If these are 32-bit values, the probability that the circuit produces the correct 32-bit signature, despite something being wrong, is maybe so small that it does not worry us. Okay, now it's very important to detect faults as early as possible. And these numbers, don't take them too seriously. They're just, rough orders of magnitude. If you detect a fault in a component, that may cost you a few dollars because the component which is bad is just discarded, and you lose that component. If you put the bad component into a board and then detect the fault at the board level, you lose more money because you spend more time testing, and also you may have to discard the entire board. Similarly, at the system level, your cost increases. And if you ship a product to the customer and then detect the fault in the field during the use of the component, it costs you more because, well, you may have to replace the customer system with a good system, and also you may have to dispatch test engineers to the customer site in order to do the testing. So the later you detect the fault, the more costly it becomes. And generally speaking, fault testing, these are two codes that are important. Because you almost never can test a circuit exhaustively, then if you test it for a long time and you don't detect any fault, that may not be because the circuit does not have any faults. It's just that your test did not detect the fault. So these are two famous codes. Trying to improve software quality by increasing the amount of testing, like trying to lose weight by weighing yourself more often. This is basically an indication of the limitation of testing. And the second one, late computer scientist Edgar Dijkstra said that program testing can be used to show the presence of bugs, but never to show their absence. In other words, if you test a piece of software for days or months and you don't detect any bugs in it, that may not be because it doesn't have any bugs. It's just you didn't come across them with your test. As I mentioned, you can't test exhaustively, so there's a limit to the effectiveness of testing. But if a software does have bugs, then appropriate testing may actually reveal some of those bugs. And we'll talk about software testing much later in the course. Okay, fault models can be considered at different abstraction levels. You can have transistor level faults, gate level faults, function level faults, and system level faults. I've highlighted gate here because our discussion, the rest of today's lecture, will be at the gate level. At the transistor level, of course, you can be a lot more detailed, but that's also the downside of this kind of testing because you have a large number of transistors in a circuit. And if you consider all the things that can go wrong with every single transistor, you have a large number of cases to study. Function level faults. So you basically test the function of a circuit. If it's an ALU or decoder or memory, you test the function. System level faults, which is malfunction in our terminology, we will discuss later in part 5 of the textbook. Okay, so let's focus on gate level faults. Now, the simplest gate level fault models are the so-called stuck and bridging models. So what are stuck faults? If you have a particular line in a circuit, okay, that line can assume logical value 0 or logical value 1, depending on the inputs that you supply to the circuit. So this is basically a full adder circuit, inputs ABC, outputs sum and carry. If this line is stuck at 0, means that this line permanently carries logic value 0, regardless of what inputs you supply to the circuit. Of course, if this is stuck at 0, then your full adder occasionally generates incorrect outputs. Of course, not the S output, because this line is not on the path to S. Notice that this line, which is stuck at 0, even though it's logically the same as this line, under normal operation, it is possible for this line to be stuck at 0, whereas these lines are not. So these carry the correct logical values, while this one is stuck at 0. So if this line is stuck at 0, the output S will not be affected. The output K may or may not be affected, because in fact, the logical value on this line may be 0. Correct value may be 0 at a particular time. So in that case, stuck at 0 fault on this line is basically ineffective. On the other hand, if this line should carry logical value 1, then it being stuck at 0 may cause problems. Okay, in order to detect this line stuck at 0, we have to try to force it to 1. In other words, provide inputs so that the proper value for that line is equal to 1. And then therefore the correct circuit will have a 1 here. The faulty circuit will have a 0. Then you have to be able to detect this difference between the faulty circuit and the fault-free circuit and this output K. There are other types of faults, line open faults. So for example, this line open. Okay, this line open may actually be equivalent to this line stuck at 0, depending on the logic technology that we use, or this line stuck at 1 actually in some case. Delay faults is when signals are delayed beyond the normal expected range. So the signal value is not incorrect. Eventually it assumes its correct value, but it's delayed beyond the design limit, and therefore it may cause incorrect circuit operation. Coupling and crosstalks are examples of other faults. So we'll focus in the rest of this discussion. Oh, bridging fault, by the way, is when two lines are, which happen to be physically close to each other in the layout, may get shorted to each other. Sometimes this shorting is equivalent to logical OR. In other words, both of these lines will assume the logical OR of the signal value B and the signal value A, but maybe also a different thing. Okay, so for the rest of our discussion, to limit the amount of discussion given our limited time, the limited time we can spend on discussion of testing, we'll focus on stuck at 0 and stuck at 1 faults. Okay, so back to this line being stuck at 0, and the question is, how can I detect this? If I can detect this, then I've detected that particular fault. Of course, I should also consider this line stuck at 1, and also all the other lines stuck at 0 or stuck at 1. So there will be a large number of different faults that I have to consider. Okay, as I mentioned when discussing the previous slide, I have to force this, I have to force this to 1. In other words, I want the value of this signal to be 1. And for this signal to be 1, this is an XOR gate, A and B must be different. So A0, B1, and or A1, B0 will force this line to 1, and therefore we'll try to force this line to 1. So this notation 1, 0 means that this line will be 1 if the circuit is operating correctly, and it will be 0 if this fault is present. Okay, we use the notation D for such a signal. This is known as D calculus. So D on this line means that normally this will be 1, but under this particular fault that we are considering, it will be 0. Okay, so now the circuit will have a different signal value on this line depending on whether it's okay or it's faulty. Now I have to be able to observe the difference between okay and faulty in this output. In order to be able to do that, I have to set this other input of this AND gate to 1. Because if this input is 0, the output of this AND gate will be 0 regardless of the value of the signal, and therefore I won't be able to observe the difference between good and bad circuit. So this must be set to 1, meaning C must be set to 1. So if this is 1 or 0, this will be 1 or 0. So this is also D. And then in order to propagate this difference, this information through the OR gate, the other input to the OR gate must be set to 0 so that I can observe the difference between good and bad circuit on this output. Now this being 0 means one of these being 0, but that's already satisfied because I said either A is 1, B is 0, or A is 0, B is 1, so that's okay. Therefore, I've determined that these two tests, A, B, C, being 0, 1, 1, or 1, 0, 1, these two input patterns detect this particular line stuck at 0. Okay, now once I've determined the test for all the faults of interest, P stuck at 0, P stuck at 1, M stuck at 0, M stuck at 1, E stuck at 0, E stuck at 1, and so on, a large number of faults, I form a table. So this is a partial table that contains the test patterns for P stuck at 0 and P stuck at 1, or Q stuck at 0 and Q stuck at 1. Okay, the full table will have a lot more columns corresponding to all the other faults. And here I see that Q stuck at 1 is detected by this test. Q stuck at 0 is detected by these two tests. P stuck at 1 is detected by this test. And P stuck at 0 is detected by these two. Notice that P stuck at 0 and Q stuck at 0 are equivalent with respect to the tests that detect them. This is sort of obvious if you look at the circuit. If P is stuck at 0, then it's like Q is stuck at 0, because if P is 0, Q will always be 0. Okay, so the two are equivalent with respect to the tests that detect them. Okay, so the next thing is, once I've constructed this table, select a minimal set of tests that detect all the faults of interest. And this is a minimization problem. So basically, I have to find out a minimal set of tests that cover, so to speak, all of these different faults. Okay, I first start usually in doing this process by faults that are detected by just one test. So this particular fault, P stuck at 1, is detected by just this one test. So I have to include this test. I have no other option. Once I've included this test, Q stuck at 1 is also detected. So I really don't need this upper test because Q stuck at 1 also is detected by this test. So I've covered P stuck at 1 and Q stuck at 1 with this test. I now need to cover P stuck at 0 and Q stuck at 0, and either of these two tests will do the trick. Okay, so a minimal set of tests with respect to just these 4 faults that I've listed in this table is this test 001 and one of these two. Let's say 101. Okay, these two tests together detect all 4 faults that I've included in this table. Of course, the real table will be much larger, more columns and more rows, and the optimization problem is a little bit more messy. Okay. Now the D algorithm has this weakness that sometimes it gets stuck, as shown in the case of this circuit. So suppose I want to detect this S stuck at 0. And this is, by the way, a multiplexer. The two inputs are X and Y, and this is the selection circuit. If S is equal to 1, X will be forwarded to the output. If S is equal to 0, Y will be forwarded. Okay, so it's a pretty common circuit, and if the D algorithm has problems with this, we are in trouble. So why does the algorithm run into problem? Okay, so here's D. Oh, by the way, I forgot to mention that. Let me go back. In trying to design test for this particular fault, we have a backward trace phase, which determines what input values will force this line to 1. And we have a forward trace phase, or path sensitization, that sensitizes the path from this location of fault to the output. The path should be sensitized or made sensitive to the change of value on this line so that that change is reflected in the output. So this part is called path sensitization, the forward trace. Okay. So basically, because we have an AND gate here, path sensitization dictates that this input should be 1, so that this change from 1 to 0 can propagate to the output. And this input should be 1. So this will be D, D and 1. This will be D bar and 1 D bar. And the output will be 1 regardless of that D value. So we really can't detect D. So what is the problem? What caused this? This is known as, the problem that caused this is known as reconvergent fan-out. So the signal D is fanned out into these two gates, and then there's the two paths reconverge into a single path here. And this reconvergent fan-out can cause problems for the D algorithm. And intuitively in this example, we were really a bit overzealous in path sensitization. All we need is to have one sensitized path from this point to the output. We don't really have to sensitize both of these paths. So if I set this line to 0, then D will not propagate, so this line will be 0 here. D will propagate through the upper line. I will have D 0, and I will have D here, and therefore the information will propagate. So the trouble came from the fact that I tried to sensitize both of these paths, whereas I didn't need that. So a modification of the D algorithm called PODEM solves this problem. PODEM is short for path-oriented decision making, and therefore it pays attention to these reconvergent fanouts and tries to not sensitize both of these in order not to run into problems later. Okay, the second method, and this is more really a method that helps us understand test pattern generation rather than a practical method for that, for test pattern generation. So what is Boolean difference? Well, we can differentiate a Boolean function much in the same way that we differentiate an algebraic function. So let's say we have this function k, which is a Boolean function of the three variable a, b, and c. And this is the logical expression for that function, ab or bc or ca. The Boolean difference of this function k with respect to b, this is sort of like differentiating a three variable function with respect to one of the variables. So the Boolean difference of k with respect to b is defined as the value of the function when b is replaced with 0, XORed, so this is definition, XORed with the value of the function when b is replaced with 1. So basically XOR, remember, is 1 when two things are different, when the two inputs are different. So basically this we are trying to determine whether the value of the function k is sensitive to b. If I change b from 0 to 1, does the value of the function change? So if the Boolean difference is 1, means the value of the function changes. If it's 0, it means the value of the function doesn't change. So the function is not sensitive to b. Okay, so f of a 0c, just replace b with 0. This term disappears, this term disappears, you get ca. XOR with b equal to 1. When b is equal to 1, you get a or c. And then this CA is redundant, we can remove it, A or C, and then we can simplify that to A, X, or C. In other words, the Boolean difference of K with respect to B is A, X, or C. So if I want to make K sensitive to B, I better select A and C in order to make this expression equal to 1. In other words, A and C should be different. 1, 0, or 0, 1. This becomes 1. And when the Boolean difference is 1, means the function is sensitive to a change in the value of b. Okay, now when faults are introduced into a circuit, this line that has a fault becomes basically an independent variable. Normally, if there's no fault, this variable p is a function of a, b, and c. But with the presence of fault, p becomes an independent variable. So basically, I can write k as a function of the primary inputs and p. So it's p or c, p and c, or A and B. So K as a function of the primary inputs A, B, and C, and this independent variable P is given by this expression. Now dk dp, remember I want to make K sensitive to changes in P, so dk dp should be equal to 1. So dk dp is basically P equal to 0, this becomes AB, XOR with P equal to 1, this becomes C or AB, and then this can be simplified to this. So this is the Boolean difference of K with respect to P. So I want to make this function equal to 1 so that K is sensitive to a change in P. On the other hand, I want to make P also equal to 1 to detect stuck at 0. Therefore, the tests that I'm interested in are solutions to this equation. P times dk dp equal to 1. I must make P equal to 1. I must make dk dp equal to 1. So this AND of these two should be equal to 1. Okay, so P is A XOR B, and dk dp is C and AB bar. So this expression should be equal to 1. So the tests that I'm interested in are solutions to this equation. Okay, for this to be equal to 1, C obviously must be equal to 1. This is the AND of three things. C must be equal to 1. So once C is equal to 1, A XOR B should be equal to 1. And if A XOR B equal to 1, meaning one of these is 1, one of the other one is 0, then this will be 1. Therefore, I don't need to worry about that. So there are two tests, both of them corresponding to C equal to 1. One of them has A0, B1. The other one has A1, B0, the same thing that we determined before. Now, tests that detect P stuck at 1 are similarly solutions to this equation. P bar, in other words, I tried to force P to 0 this time, but dk dp must still be equal to 1. In other words, K must be sensitive to a change in P. So again, this is the equation, and the solution is C equal to 1 and A equal B equal to 0. So there's just one test in this case. Okay, so this is a very nice formulation. It converts the problem of test generation, finding out what tests detect a particular logic fault of interest, to the problem of satisfiability. Satisfiability is basically trying to see whether we can satisfy a particular logic equation. In other words, choose the variables so that the value of this logic expression becomes 1. Okay, of course, we know that satisfiability is an NP-complete problem, and therefore this gives us a hint that testing is also a difficult problem. Although this is not the proof that testing is NP-complete, because we showed that testing can be converted to a problem that is NP-complete. We really should do the opposite. In other words, we should show that an NP-complete problem can be converted to testing in order to show that testing is NP-complete. But that's in fact the case. We can prove that testing is NP-complete, and I'll show you the proof in a few minutes. So the satisfiability problem, this is basically a decision problem, is a Boolean expression satisfiable? In other words, can we choose values for the variables in that expression to make the result equal to 1? This is known to be NP-complete. It was proved a long time ago by Cook in 1971. In fact, Cook also proved that this special case, seemingly simpler case of satisfiability, known as 3-SAT, is also NP-complete. 3-SAT is basically satisfiability with a logic expression that is a product of 3-term OR clauses. In other words, it's a product of clauses. Each clause has only 3 terms in it, 3 variables or complemented variables in it, and they're ORed together. Okay, so we just saw that Boolean difference formulation converts fault detection to the SAT problem. To prove NP completeness of fault detection, we need to show that SAT or some other NP, any other NP complete problem can be converted to fault testing. And this proof is due to Ibarra and Sani, 1975. A simple alternate proof by Fujiwara is in the textbook. If you are interested, you can read that. That's much simpler than the original Ibarra and Sani proof. Okay, so this is an outline of the proof. We know that 3-SAT is NP-complete. In fact, 3-SAT with the further restriction that each of the clauses is monotone. In other words, a clause is monotone if it contains the 3 terms, the 3 terms it contains are either all complemented or all uncomplemented variables, but not both at the same time. So this is basically a special case of 3-SAT, which is also known to be NP-complete. Okay, now closed monotone SAT can be converted to fault detection in a circuit, and the remaining steps of the proof basically show that. I won't go through this. The details are in the textbook if you are interested, and you're not required to do it unless you are curious to see how such proofs go. So fault detection is NP-complete, meaning it's a difficult problem, and we don't have good algorithms for it, efficient algorithms for it. Algorithms tend to be exponential in time. So we need heuristics. Like any other NP-hard problem, we need heuristics for fault testing, and there are a whole bunch of heuristics available for it. Now, so far we've been talking about testing combinational circuits. If circuits are sequential, in other words, they have memory, testing becomes much, much harder because the presence of memory flip-flops provides the circuit with states, and therefore not only we have a large number of input patterns, the circuit can be in a large number of possible states, and the combination of a large number of inputs and a large number of states basically makes fault testing much harder. So when we apply an input sequence, the circuit moves through its states, and therefore we have no idea which state it's in, and therefore not only we have to apply inputs to exercise different parts of the circuit, we have to exercise the circuit moving through different sequences of states. Okay, so it's much, much harder. Testing of memory is a subject that has received a lot of attention because memory is basically a common component of many digital systems. So if you have, let's say, an SRAM or DRAM, how do you test it to see that it's working correctly? A simple-minded approach would basically write the all zeros pattern and all ones pattern into every memory word. The thinking being that if we can store zeros, all zeros, and all ones in a memory word, that means the individual cells can be changed to 0, they can be changed to 1, therefore they should be okay. Well, there's a lot of problems with this argument. First of all, this approach does not test the access and decoding mechanism. When you write into a particular location in memory and say, okay, I could store 0, read out 0. I can store 1, read it out, notice that it's all ones. But how can you be sure that this pattern was stored in location 1000, for example, that you're trying to test? Because if the decoding circuitry doesn't work correctly, then this may be stored in a different location and read out from that location. So you tested another location, not location 1000. So that's one problem. Many memory faults are pattern sensitive. In other words, this cell, when you store all zeros, it works correctly. When you store all ones, this cell can be changed to 0, and it can be changed to 1. But whether or not you can change the cell from 0 to 1 or vice versa may depend on the contents of neighboring cells in memory. These cells are so close, so tightly packed to each other, that sometimes it generates pattern sensitivity. In other words, whether or not you can reliably store a 0 or a 1 in a cell may depend on the contents of neighboring cells that are very close in space. So this pattern sensitivity means you have to test a lot more cases to have a reasonable confidence that the memory is working correctly. Furthermore, memories tend to have dynamic faults that are exposed for specific access sequences. So if you store this pattern in a word, then a different pattern, then a different pattern, that sequence of patterns may actually reveal a fault in one of those memory cells that does not exist for a different pattern of values stored. So these are dynamic faults. So to summarize, testing memory is non-trivial, and there's a lot of research on the topic, different strategies. Of course, none of these is completely foolproof because we cannot test memory exhaustively given all these dependence on, the pattern sensitivity, dynamic faults, and so on. But there are good heuristics that allow us to develop reasonable confidence that the memory is working correctly after we have put it through. And in fact, this is done when you boot up a computer. Part of the boot up process is subjecting the memory, or at least part of it, to rigorous testing, and then using that part of the memory that was tested in order to run diagnostics on other parts, the CPU and so on. Okay, that's enough for us to know about memory testing. Just remember that it's non-trivial and a lot of research has gone into it. Okay, this section has not been written yet, so nothing to talk about. I'm gonna go now to chapter 11 and discuss a little bit design for testability. So if testing is difficult, we better not design a circuit and then worry about its testing, because it may be very difficult to test. We should aim to build testability into our circuits. In other words, design the circuits to be easily testable. Okay, so that's the topic of this chapter. As I mentioned before, a complex unit such as a microprocessor cannot be tested solely based on its input and output behavior, because it has many inputs and many outputs, and you cannot exhaustively test a microprocessor. Okay, so you have to have a strategy, a heuristic, to design a test that does a reasonable job of detecting faults in the microprocessor. So we should design the microprocessor or any other complex unit with testability in mind. Okay, as I mentioned before, testability is a function of two things: controllability and observability. In order to be able to test whether point A in a circuit is faulty, we must be able to control that point from primary inputs, and we must be able to observe that point on primary outputs. Okay, later we'll talk about controllability and observability in quantitative terms. Right now it's just qualitative. Point A is controllable if we have reasonable control over it from the input, and it's observable if we can observe that point reasonably well through the output. Okay, so let's now try to quantify controllability. There are other ways of quantifying controllability, so I'll just discuss one method to just give you a sense of what this is about. So the controllability of a line in the logic circuit is a number between 0 and 1. 0 means it's not controllable at all. 1 means it's fully controllable. And numbers in between basically are sort of intermediate values. Okay. A primary input of a circuit is fully controllable. So in this circuit, you see controllability of this line is 1. That's probably a primary input of the circuit because I can put any value I want on that input. Therefore, I can fully control this particular line. These other two lines are not fully controllable. They have smaller than 1, values that are smaller than 1. So they probably come from other circuit components. Okay, so suppose I've already determined the controllabilities for these three lines, inputs to a 3-input AND gate. What is the controllability of the output of that AND gate? So controllability quantification proceeds from inputs to outputs. We start from the inputs, assign them controllability of 1, and then proceed through the circuit and assign controllability values to other lines in the circuit until I get to outputs. Okay, for a gate or other logic element, we define what is known as a controllability transfer factor. For this gate, I'll show you how it is derived. It's 0.25. So if the controllability transfer factor is 0.25 for this gate, the controllability of its output is the average of input controllabilities times the controllability transfer factor. So the average of 1, 0.3, and 0.5, these are 1.8 total divided by 3 is 0.6. So 0.6 times the controllability transfer factor, which is 0.25, gives you 0.50. Okay? So the only remaining thing is to show you how we derive this controllability transfer factor, because the rest is just mechanical. If you have the input controllabilities, and if you have the controllability transfer factor, you just multiply the average input controllability by the transfer factor to get the output controllability. Okay, the controllability transfer factor for a gate or other circuit element is defined as this 1 minus the number of input patterns that force the output to 0 minus the number of input patterns that force the output to 1 divided by the sum of those two values. Now for an AND gate, there are 8 possible input patterns, 7 of which force the output to 0, and 1 of which force the output to 1. Okay, the only way to make the output equal to 1 is to have 1, 1, 1, all 3 inputs equal to 1. So one of the 8 input patterns makes the output equal to 1, 7 make the output equal to 0. So 1 minus 7 minus 1 divided by 7 plus 1. So 7 minus 1 is 6, 7 plus 1 is 8, 6, 8 or 3/4, 1 minus 3/4 is 1/4. Okay, intuitively, this has poor controllability transfer because it's much easier to make the output equal to 0 than to make the output equal to 1. If I had an XOR gate, an XOR gate has 2 inputs and 1 output. 2 of the 4 input patterns make the output equal to 0. 2 of the 4 input patterns make the output equal to 1. So if I use this formula, I will have 2 minus 2, 0. Controllability transfer factor is 1 for an XOR gate. Okay, and that's because in an XOR gate, it's equally simple to make the output equal to 0 and to make it equal to 1. And therefore, networks built of XOR gates have good controllability for their internal lines, whereas networks built of AND and OR gates basically lose controllability as we proceed through the circuit. These numbers become smaller and smaller as we get deeper and deeper into the circuit. Okay, now an important point here is that these numbers do not have any physical significance. In other words, here you see a controllability 0.3, this one 0.15, which is half of that. The fact that it's half of that bears no physical significance. It's just sort of an indication this has poorer controllability compared to this one. So that's the only thing these numbers indicate, whether controllability between 2 lines, comparing them, whether one is better than the other one. Okay, the actual numerical value has no physical significance, no interpretation, other than a smaller number is worse than a larger number. 1 is, of course, ideal for controllability. Okay, so if we have a circuit and we notice that this point in the circuit has very poor controllability, we can insert a test point there. In other words, this is a test point, and through this control point, I can control this point. Okay, so normally I have to control that point through primary inputs, and because signals go through a large number of logic levels, controllability is poor. If I insert this test point, so that I sort of decouple this signal from this point, and then provide an external access point so that I can control. So in testing this blue part, I now have full control over this line, and therefore it's easier to test this part compared to the case where I had to test this part by providing inputs through this yellow box. Okay, so poor controllability is an indication that I perhaps want to insert a test point over there. Okay, now observe, oh, by the way, fan out, if the controllability of this line is C, then the controllability of these fan out branches is, this is an empirical formula. Again, it has no physical significance. Is C divided by 1 plus log 2f. So for example, if this branches out into 2 lines, the fan out, f will be 2, log 2 will be 1, so it will be C over 2. So if this were a two-way fan out, each of the branches would have controllability C over 2. For three-way, it's a little bit less controllability. Okay, so basically it means I cannot really control these three lines very well individually. They're, whatever I put here will go on all three of those. So individual control is lost over those lines. But why this particular formula? That's empirical, and that's been shown to work well in practice. Okay, observability is similar, except for observability, we move from the output toward the input. So a primary output line has perfect observability of 1, and then we move backwards by computing what is known as observability transfer factor for various circuit elements. So if I know that the observability of this line is 0.6 and the observability transfer factor for this box is 0.25, then each of these observabilities will be 1/4 of this. So this is, this has fairly good observability, 0.6. It's not perfect, but these have worse observabilities because they have to go through this gate before getting here. So how do you compute observability transfer factor? So observability of input is observability of output times observability transfer factor. 0.6 times 0.25 is 0.15. Observability transfer factor is given by this equation. This is the number of input patterns that sensitize the path divided by number of input patterns that sensitize the path plus the number of input patterns that inhibit the path, do not sensitize. So this is basically total number of input patterns. So the more input patterns sensitize the path, the larger the observability transfer factor. So why is it 0.25 here? So suppose there's a fault on this line, on the top input to this AND gate. In order to sensitize the path, I have to set both of these other inputs to 1. So one of the 4 patterns sensitizes the path. 3 of the 4 patterns do not sensitize the path. So the number of patterns that sensitize the path is 1. The number that inhibit the path is 3. So this is 4, total number of. So 1 divided by 4. So again, because this is an AND, if this were an XOR gate, okay, and it had 2 inputs, and this were stuck, then no matter what I put on the other line, 0 or 1, the output will depend on this. Okay, so if this is D, using the D calculus notation, this is XOR. Okay, imagine this is XOR. One input is D, the other input is 1, then this will be D bar. If this is D and this is 0, this will be D. Okay, so the output in both cases depends on the faulty input, and therefore the observability transfer factor for XOR is also 1. Okay, so XOR is pretty good with respect to testability in circuits because it has controllability and observability transfer factors of 1. Again, for fan out, if you have the observabilities of the output side of the fan out, you get the observability of the input using this equation. So suppose each of these has observability 0.5, 0.5, 0.5, 0.5. So each of these terms will be 0.5, 1/2. The product will be 1/8. This will be 7/8. So observability of this line is better than those because basically you can observe this through 3 different paths. So these will go to different parts of the circuit. And therefore, even though observability of these lines was 0.5 each, this one will be 7/8. Okay, again, there's no physical significance to why this formula is used. It has been demonstrated to work well in practice. It's an empirical formula, and therefore it is used. Again, if the observability of this point is poor because it has to go through this blue part of the circuit to get to primary output, I can provide an observation point here by basically making the signal go to here and then be observed through here. Okay, so the test point can be used for observation point or also for control point, depending on the signal. If you set the signal equal to 0, you decouple the signal from the other side, and this becomes a control point. If you use a 1 here, you propagate this, and then you can observe the signal directly without it having to go through more circuitry. Now, controllability is basically the product. Testability. Oops, I have to go in the other direction. Testability is the product of controllability and observability. The intuition being that good testability requires good controllability and good observability. So if both of these are equal to 1, testability will be equal to 1. If one of these is equal to 0, then testability will be 0. If this is 1/2, this is 1/2, then it will be 1/4. Okay? So in the previous examples, we obtained these controllabilities for the input and output lines of an AND gate, and these observabilities. You simply multiply these, 0.6 times 0.15. And then you can see that among these lines, this one has the worst testability. This one has the best testability. Okay, again, the relative magnitudes do not have any physical significance, just the fact that this is the smallest number means, so if I had just one, if I had enough room for just one test point, then I better put that test point over here because it has the smallest testability. Okay, if I want to put 2 test points, then perhaps I can put the 2 test points on this. So normally I'm dealing with a much larger circuit, so I look for points that have poor testability in order to decide where to put the test points. Okay, let me skip this slide. Now, in order to improve the testability of sequential circuit, one of the methods is the so-called sequential scan technique. What is this method? So this is a typical sequential circuit, which has a combinational part and a bunch of flip-flops that are fed, that are set by the combinational part, and also they affect the operation of the combinational part. So that if you provide some input and these flip-flops are in a particular state, then the output will be determined as well as the next state of these flip-flops. So this is sort of an abstract model of a sequential circuit. The problem, as I mentioned, for testing sequential circuit is that when you provide the input and these flip-flops have a particular state, while you are testing the combination, let's say 0, 0. You're testing the combinational circuit with these inputs being 0 and 0. Then in the next time step, this may become 0, 1. So now you have 0, 1. So the next test will be applied at 0, 1. It would be nice if you can test the 0, 0 state with other inputs. Okay? This is done by providing a mechanism for you to be able to set desired values into these flip-flops, because the values into those flip-flops are dictated by the operation of this combinational logic and input. They are not fully under your control. Okay, so you have poor controllability over those flip-flops. Now, if you provide here switches so that under normal mode, this signal is routed to the flip-flop and this signal is routed. So the normal connections are established in the circuit. During a special test mode, you can supply through this line an arbitrary value to go into this flip-flop. And then basically by shifting a sequence of values, you can set those flip-flops to an arbitrary pattern. So for example, if you shift in 0, 0, the flip-flops will be set to 0, 0. And then you supply some input. Basically, you are now testing the combinational logic with those flip-flops being 0, 0. You don't let those flip-flops change. You maintain the test mode. And therefore, you supply another input and test the combinational logic again with those flip-flops being 0, 0. So this basically gives you full control over the contents of those flip-flops as you try to test the combinational logic. Of course, you have to supply a lot more tests because then you have to test for the case of 0, 1, 1, 0, 1, 1, but at least you have control over the contents of those flip-flops. Okay, if a circuit has a lot of flip-flops, then perhaps you don't want to put all of them in this scan path, because then it takes a long time to shift values into them. By the way, as you shift new values into the flip-flops, you also read the old values that were. So this is like a shift register. You shift a new set of values and you read out the contents to see what was generated by the combinational circuit and put into the flip-flop. So if there are too many flip-flops, then perhaps you can decide to use a subset of the flip-flops, the ones that are more critical in some way, into the scan path in order to reduce the length of the scan path. And then these two perhaps are not all that critical and you leave them out. So that's partial scan design. Okay, so scan design allows you to have good controllability and observability. Okay, you can control the contents of the flip-flop by shifting arbitrary values into them. And at any time, you can view the contents of those flip-flop as you shift out the values through this path and see what was in those flip-flops. So improve the controllability and observability of the flip-flops. Okay, this is one way in which this idea can be used for testing a component. So suppose you have a simple chip. Of course, chips normally have many more inputs and outputs. But let's take a toy example in which we have 5 parallel in pins into the chip, 5 parallel out pins, and some control pins. So basically, you can test the digital circuit, whatever it is here, by putting a desired pattern into these cells. Therefore, apply an arbitrary input pattern that you want to this digital circuit and then observe the output. So you scan in a particular pattern to be used as input for this digital circuit, and then you observe the output through the scan out. Mode select basically says whether we are in normal mode. In normal mode, basically, inputs, primary inputs are led to the circuit. So these boxes become transparent as if they're not there. Inputs are supplied to the circuit and the outputs go out, normal mode. Under test mode, then these boxes do not let inputs to go through, but take values from the scan path. And this is an example of how you can use multiple components on the circuit board by cascading together their scan path. So the scan path for this component is connected to the scan path of this one, to the scan path of this one, and then to the scan path of this one. So you have one huge scan path that basically encompasses all four components on this particular circuit board. Okay, so this is the design, or one particular design for these yellow boxes that you see in this diagram. So when you want those boxes to be transparent, you set this multiplexer so that data in goes directly to the chip, or the chip output goes directly to the pin, output pin. When you want to do the scan part, then you scan in. So this is basically the scan path. You scan in arbitrary input into this flip-flop, and then from there to the next one, you shift in whatever you want. Meanwhile, as you are setting the contents of this flip-flop, this one is isolated and is holding the old values. So you can overlap the scan input with the previous test. So previously you put some set of values here, and you are now testing the circuit with these set of values through the test path, the green path. But simultaneously with that test being in progress, you are shifting in a new set of values so that when that test is over, you simply transfer these values here and now use those for testing while you input yet another set of values. So this saves time because you overlap the shift in and shift out of the scan pattern with the actual testing. This is sort of a leader-follower arrangement. So you set the leader to whatever pattern you want, while the follower is keeping its old contents and is using it in the test mode. And then when this test is complete, you transfer these new values here, do the new test while also loading a new set of values into the scan path. Built-in test, self-test instead of test pattern being applied from outside. The circuit that you build, the chip that you build, has an internal test pattern generation circuit capability. And then once in a while, when the circuit is idle, the test pattern generator supplies it with tests and then decides whether it did well in that test. So the idle cycles of the circuit are used internally to the chip by this built-in self-test capability to ensure that the circuit is working correctly. Okay, so this is all I wanted to say for testing, fault testing, and design for testability. In the next lecture, we will talk about fault masking and some practical methods for using it in actual digital circuit. Bye for now. Stay well until the next lecture.